Hello everyone, welcome once again to Subject Math. Our topic today is simple AC circuit. What is an AC circuit? An AC circuit is a circuit in which an alternating current flows. A circuit in which an alternating current flows. An alternating current is usually of this form. Alternating current is a type of current that changes direction periodically or sinusoidally, as you can see. While a DC circuit, on the other hand, is a circuit in which a direct current flows. And the direct current is usually something like this. As you can see, there's no change in direction, so a steady flow of current. So this is a DC. This is what a DC current looks like. It's just steady in one direction, while that of AC is sinusoidal. You can see it going up and down like a wave. So that's basically the major difference between AC and DC circuit. AC current is what we make use of in our homes. Our socket in the house uses AC current. Our fans, our refrigerators also uses AC current. Fans, refrigerators, they make use of AC current. While DC, on the other hand, we have our TV, our television, our chargers, our phone chargers, our laptop chargers, they make use of direct current. Okay, quickly, we're going to consider some terminologies used in describing AC circuit. So the first one here is instantaneous current. And we said instantaneous current is the current at a particular time t. If you remember, just like we have instantaneous speed, we said it's the speed at a particular time t. The same thing is applicable here. The current at a particular time, at a particular point in time. That's what instantaneous current is. And it's given by I is equals to I naught sine Wt. I is equals to I naught sine Wt. I here is the instantaneous current. I is equals to instantaneous current. I naught is the peak value of the current in an AC circuit. Wt is called the phase angle. Now I'm going to come back to I naught, which is the peak value. I naught is equals to peak value, which equals to the maximum amount of current that flows in an AC circuit is called I naught, which is the same thing as peak value of current. Maximum amount of current in an AC circuit. Okay, so the peak value of current, which is I naught, is defined as the maximum amount of current in an AC circuit. And it's given by I naught is equals to square root of 2 times I Irms. So I can as well write it as I naught is equals to I Irms root 2. So this is like the mathematical statement that defines the peak value of the current. So my question now is, what is Irms? Okay, Irms. Irms means the root mean square value of the current. You know, I said that the peak value of current is the maximum amount of current in an AC circuit. While this is in an AC circuit, this actually gives us the same value of this in a DC circuit. So the root mean square value of the current in a DC circuit is the same current that produces the same heat effect, the same resistance in a DC circuit. So IRMS deals with direct current circuit, while I naught, which is the peak value of current, deals with alternating current circuit. The same effect that will be produced by the I naught is equal to high RMS, but in a DC circuit, in a DC circuit, in a direct current circuit. I want to believe that is very clear. Also, IRMS, just like what we have here, IRMS is given by I naught over root 2. And don't forget, both of them, you know the unit of current is ampere. So both of them are measured in amp. Its unit is ampere. Now we all know capital A. Same as this. Its unit is ampere. Both of them are measured in ampere, which is capital A. Just like we have instantaneous current, we also have instantaneous voltage. Instantaneous voltage is the voltage produced in an AC circuit at a particular time, just like I explained instantaneous current earlier. So, and it's given by V is equals to V naught sine WT. Very similar to that of the current. This is our instantaneous voltage. Where V naught is the peak voltage. That's the maximum voltage produced in an AC circuit. And WT here is the phase angle. That's the angle between the voltage and the current. Okay, so the peak voltage here, just like that of the current that I explained earlier, V naught is equals to root 2 V RMS. And the V RMS is the root mean square value. V RMS is equals to the root mean square value of the voltage that is the same voltage produced by a DC circuit as compared to that of an AC circuit. Same voltage that produces the same effect as that of an AC circuit is called the RMS voltage, which is given by VRMS is equals to V naught, which is the peak voltage over root 2. So let's take note of that. Very, very important. So let's solve some problems involving instantaneous current and voltage. The first one I have here says the current I in an AC circuit is given by the equation I is equals to 30 sine 100 pi t. Okay, so solution. The first thing I'm given here is this. I is equals to 30 sine 100 pi t. If you look at this equation and you compare it with the one I gave us initially, which is this, you agree with me that both of them are similar. So the current that we are given here is the same thing as our instantaneous current. So from this question, they said where t is time in seconds, deduce the following from this equation. The first one, frequency of the current. So basically what we are just going to do here is to compare these two equations. I have this, I'm going to compare. By comparing with, you compare it with this. I'll just write it under it. I'll write this. I'll write this underneath. The one we are given. This is 30 sine 100 pi t. So I naught is the same thing as the peak. Okay, let me just start with the first question, which says frequency of the current. To get the frequency, I'll come to the latter part of the equation, which is this. I'll compare these two. So the first one is the frequency. Now, to get my frequency, I'll compare these two. Wt is equals to 100 pi t. T here cancels t. So I have W is equal to 100 pi. But you recall, from our simple harmonic motion, recall that W is equals to 2 pi f. So wherever I see W now, I'm just going to put 2 pi f. So I'm going to rewrite that as 2. So I'm going to rewrite this. W equals to 100 pi as 2 pi f is equals to 100 pi. So pi cancels pi, and and then F equals to 100 over 2. And that gives me 50 Hertz. Frequency is measured in Hertz. So my first answer, the frequency of the current is 50 Hertz. I want to believe that is very explanatory. Okay, so the second question here says the peak value of the current. That's very simple. Compare the two equations again. And here I have I naught. So the peak value of the current from here, peak value of the current, I naught is equals to 30. Peak value is the same thing as I naught, which equals to 30 amp. So that has been answered, 30 amp. Then the last one says the RMS value of the current. So remember our formula. IRMS is equals to I naught over root 2. Our I naught here is 30 over root 2. So by the time we solve this, using rationalization of sort, mathematics students, okay, we multiply by root 2. So I have 30 root 2. Root 2 times root 2 will give me 2. 2 here 1, 2 here 15. So I have 15 root 2 amp as my RMS value of current. So high RMS is equals to 15 root 2 amp, which is the same as 21.21 ampere. Another example here is this. If an AC is represented by I equals to I naught sine WT, calculate the instantaneous value of the current. Take note of that. If in the circuit it has RMS value of 15.0 amp and phase angle, so let's write out our parameters. First, we are given the RMS value of the current, IRMS, which equals to 15 amp, and then we are given the phase angle, which equals to 30 degrees. And it asks us to calculate the instantaneous current, which is I naught. So we come back here. This formula says I equals to I naught sine WT. Do we have our I? No. I naught? No. But we have sine WT. So first, we have to get the value of I naught. And you remember the formula that says I naught is equals to IRMS root 2. So it's just going to be 15 root 2, which equals to 15 root 2, which equals to 21.21 amp or ampere. So we found the value of I naught. We can substitute it into this equation now. Don't forget that we are asked to calculate the instantaneous value of the current, which is this. So our instantaneous value of current is equals to I naught sine WT. Our I naught is 21.21. Then sine our WT is 30 degrees. If you multiply sine 30, we give us 0.5. Multiply by this, we will have 10.61, which is equals to our instantaneous current. Instantaneous current. So I want to believe that is very, very explanatory. Resistance in an AC circuit. Resistance in an AC circuit. Okay, so this is a typical example of what an AC circuit, including the resistance, has, or an AC circuit with a resistor has. Here is the symbol for resistor, this box here. Now this symbol here stands for alternating current. This is the ammeter here, this is the resistor, and this is the voltmeter, always connected in parallel to the resistor. Okay? So according to Ohm's law, you recall that Ohm's law, from Ohm's law we have this V is equals to IR, where V is our voltage, I is the current, and R is the resistance. So from here, resistance equals to V over I. So this is what we have, resistance in an AC circuit. So let's take note of that. And I also want us to take note that in an AC circuit with resistance only, that we have the maximum value of the current, and at the same time we have the maximum value of voltage. So the current and the voltage are both maximum. So let's take note of that. That means both of them are in phase. They are in phase. The current and voltage are in phase. Both of them have the same maximum value. Resistance in a capacitive circuit, like what we have, this symbol here represents a capacitor. Like I said earlier, this represents alternating current. This is the ammeter, this is a capacitor, and this is a voltmeter. So when you have a capacitive circuit like this, the resistance, which is the opposition to current flow in this circuit, is giving us this VRMF. RMF is a RMF, just like what I wrote earlier, and is equivalent to 2 pi FC. And another name we call this is we call it the resistance in a capacitive circuit, which is equals to reactance in a capacitive circuit. A capacitive circuit is a circuit that contains a capacitor. So take note of this formula. It's very, very important. So I'm just going to write it as X C is equals to 1 over 2 pi FC. And this is what we call the reactance. Of a capacitive circuit. Where C is the value of the capacitor. Value of the capacitance, sorry. C is equal to capacitance. And the unit is in farad. Of course, you know 2 pi f is the same thing as our phase angle, which is the same thing as W. F is the frequency, and that is measured in hertz. So here is the phasor diagram of a capacitive circuit. As you can see, the current leads the voltage by 90 degrees. By 90 degrees. So the current leads the voltage by 90 degrees. Or you could write it the other way, which is the voltage lags the current by still the same angle, 90 degrees. So don't forget that in a capacitive circuit, current leads the voltage by 90 degrees, or the voltage lags. Take note of those two words. Leads, lags the current by 90 degrees. Very important. Okay, so this is what an inductive circuit looks like. Here, as usual, is our voltage connected in parallel. Here is the inductor. You can see the coil, induction coil. Here is the ammeter, and here is our AC symbol, alternating current, connected to the circuit. Now, in an inductive circuit, resistance, just like we said earlier, is giving us which is the same thing as 2 pi f L. I can as well write it as W. You know 2 pi f is W. I can just write W here. So in other words, the reactance in an inductive circuit. This is the symbol for reactance. X for inductive circuit is X subscript L, but for capacitive circuit is X subscript C. So for an inductive circuit is 2 pi f L, where L is the inductance. And the unit is in Henry, is measured in Henry, while F is frequency, measured in hertz. So please, very important, you don't mix this up. This is inductive reactance. While this one up here, 1 over 2 pi Fc, is capacitive reactance. This is for a capacitive circuit, the one I treated earlier. And for the inductive circuit, we have XL equals to 2 pi FL as our reactance. And another name for reactance is resistance, opposition to current flow in a circuit. In an inductive circuit, we use X subscript L, while in a capacitive circuit, we use X subscript C. Okay? So, I'm just going to draw the phasor diagram of an inductive circuit. So here is the phasor diagram. You will observe that here, for an inductive circuit, the voltage comes before the current. So that implies the voltage leads the current by 90 degrees. Or the current lags the voltage by 90 degrees. Take note of those two words, lead and lag. So I can write this as the voltage. So note the difference. For an inductive circuit, voltage leads the current. But for a capacitive circuit, the current leads the voltage by 90 degrees. Very important. Voltage leads the current by 90 degrees. Or you could write it as the current lags the voltage by 90 degrees. So take note of that. Voltage leads the current by 90 degrees in an inductive circuit. The first example here says, calculate the inductance L of the coil connected in the circuit diagram shown below. Here is the inductor, here is the ammeter, and here we have the alternating current, the voltage, and the frequency. So from that diagram, we have our current to be 2 amps. We have voltage to be 240 volts. Frequency is 100 over pi hertz. From Ohm's law, you recall that V is equals to this. R from here is V over I. And we said that R also is equals to our reactance. In this case, this is an inductive circuit. So it's our inductive reactance. So I'm just going to substitute this into the so V is our 240 volts over the the high, which is the current, and that gives me 120 ohms. So my reactance, the inductive reactance, XL is equals to 120 volts. So having found that, I can go ahead and find my inductance L using this formula. XL is equals to 2 pi f L, which equals to our XL from here is 120. 2 times pi times the frequency is 100 over pi times L. Don't forget, we don't have L. L is what we are being asked to calculate. So pi cancels pi. So I have 120 is equals to 200 L. Divide both sides by 200. This cancels this. This cancels this. So my L here is 12 over 20, which equals to 0.6 Henry. The unit of inductance is Henry, capital H. So L is equals to 0.6 H. Basically, reactance has two formulas. We could use this or this, depending on what we are given. In case you don't have the inductor, then you can use current and voltage to get the reactance, just like I did earlier. But in the other case, when you are given the inductance and you are given the frequency, you can just come and use this particular formula. Another example here is a capacitor or capacitance 2.5 mil farad is connected to an AC power source of frequency 200 over pi hertz. Calculate the reactance of the capacitor. Calculate the reactance of the capacitor. So I'm just going to write out our parameters. The first one says that the capacitance is 2.5 mil farad, which is the same thing as 2.5. Mil is 10 raised to power minus 6 farad. We are given the frequency, which is 200 over pi hertz. Now we are asked to find the reactance, XC. So I'm just going to go ahead to use either this formula or I could use this or this, depending on what you are given, like I said earlier. So if you look at the parameters now, we have C and F. Here we don't have C, we don't have F. So automatically it means we cannot use this formula. In this case we have C, we have F. So that means we are going with this formula. Our XC therefore is 2 pi times frequency 200 over pi times C, which is 2.5 times 10 raised to power minus 6. Pi cancels pi, so I have 1 over 400 times 2.5 times 10 raised to power minus 6. And that will give me 1000 ohms. It's that simple. So our reactance is equals to 1000 ohms. It's in ohms because it measures the opposition to the current flow, just like resistance. So I want to believe that is very, very explanatory. Here are some exercises that you can try out. Thanks for watching.